Welcome. You can see that we have we're starting with our sort of general formula sheet. It's got a little bit more on it, although not much more, because remember, most of the changes that we made to move from a blank formula sheet to the formula sheet that we have in front of us was done during the kinematics portion. So most of this is kinematics. Let me go with a lighter color. So we've added this when we first started forces, with this right here being our main formula. And that's such a main formula, we're going to give it the finger. There we go. So that is a major formula. And by me saying a major formula, that's a little bit misleading. It's not just a formula. In fact, we'll be using this today in a lot of different ways. This is sort of a build it yourself. This is almost the DNA of force formulas. So from that formula, you can create all sorts of other formulas. A couple more that might look familiar to you. We haven't used them yet in any of these recordings, but we'll be talking about them today, and we'll be revisiting them today as well. Or we'll be visiting them today and a few times. Just to review our problem-solving method, I'm not going to spend much time on this, but again, notice the importance of that one formula. Even if objects aren't accelerating, we still use that formula. It's just a special case where the acceleration is equal to 0. So let's start on a very simple problem and use this to introduce friction, the concept of friction and the concept of a frictional coefficient. So if I were to ask you, what is the frictional force acting on a box? So if we have a box sitting on a floor, and I were to ask you what the frictional force was, you wouldn't be able to answer that question, because that frictional force depends on some of the other forces. So if I exert a very weak push on this right here, so I'm just going to make a very tiny arrow, and we'll say that's the applied force. If this object is, so it's a very weak push, it's a 120 kilogram box, so qualitatively speaking, it makes sense that a very weak push is not going to do anything to a 120 kilogram box. That's over 250 pounds. So we've got a box with a football lineman hiding in there, or a shot putter hiding in there. If this is the case, then the frictional force, which is often designated by a script F, so F-A-P-P, it's not the force of the apple, it's the applied force. And lowercase f is the frictional force. So if I wanted to give the full name of the applied force, that would be the contact push of the person on the box. This would be the frictional push of the floor on the box, or the frictional pull. What would be a better way to say that? Probably push, frictional push of the floor on the box. So that's a very weak push. So now we're exerting a weak push is that too big of a push for a weak push? I will go with that. So here's the applied force, and I apologize, I didn't draw this very well. I have my arrow up in the air here. And now a medium push. And of course this is qualitative, right? So what is a medium push? If I'm competing against a shot putter to push, her medium push might be my super duper strong push. But notice we've got the same person pushing each time, and this person does not look like a shot putter. So here's our applied force. Here's our frictional force. So notice in each of these cases, F applied equals the frictional force. You might say, okay, they're in opposite directions, so maybe a better way to say this is actually represent them as vectors, but take the magnitude of the vector, because we know they're in opposite directions. So one push, it's a 10-pound push to the left, the other one's a 10-pound push to the right. So these are two different ways of saying the same thing. And that is the equivalency no matter what the push was. So notice the frictional force varies depending on the applied force. And that's interesting. Both times I spelled the word applied, I forgot the I, so I put the little dot there to make you think that I remembered it. Sorry about that. So now the maximum push. Let's just say this is the person's maximum push. So this is the applied force, but it's the maximum. The idea behind this is, okay, what is the biggest push that can be exerted such that it overcomes this frictional force here? So if we push strong enough, so the friction force can be overcome. So this then becomes our maximum force. And because this is not moving, so notice that this is stationary, this is stationary, this is stationary. This is stationary just until the force is overcome. So what we've got here is what's called the static friction force. So this friction force is called the static friction force. And that's F sub S. I'm going to switch to a different color just to kind of organize things better, otherwise it'll look a little bit too messy. So we notice that the frictional force is not always the same. If we go back to this, we noticed a couple things here. So here is the static friction force. You notice for one thing, it's got this less than or equal to sign. It's got the normal force, and it's got some sort of a constant here. So first off, it makes sense that if this object here were more massive, that it would be more difficult to go from stationary to not stationary. So it turns out that that frictional force is proportional to the normal force, so the contact push of the floor on the object. And in case you've probably seen, most of you have seen this before, this just means is proportional to. We also noticed that the frictional force is not always the same. So, and actually, let me just say that right now all we can say is the maximum. I'm going to delete what I have here. I kind of crowded things in. Sorry about that. So Fs max, which we like to call Fs max. So Fs max is proportional to n. We also notice that sometimes the static friction force is less than the normal force. So in this first case, for example, or this second case, the normal force didn't change from the first case to the second case. So the normal force is the same here, and here, and here, and here. What changed was the frictional force, and that changed because the applied force changed. So notice the frictional force is getting bigger in each of these cases because the applied force is getting bigger. So that's another observation. If we combine these two things together and we change this into an equality, Fs max sometimes is less than, so Fs max is not equal to the normal force, it's equal to some constant times the normal force. And that constant here is called the coefficient of friction. And this is the Greek letter mu, corresponds to our letter m. Let me get rid of that stray dot here. And so combining this equality, or the fact that it's proportional to the normal force or equal to mu times the normal force in general, Fs is less than or equal to mu sub s times the normal force. So this formula here describes what I just talked through when I went over each of these things right here. So what I just talked you through with the boxes is typified by that equation right there. And this coefficient, it depends on the two materials. So if we have, and if this is a box, so a box could be a wooden crate. And I just copied and pasted this table, by the way, table 5. I just copied and pasted it from the book. So what would be reasonable on here? Maybe a wooden crate on top of a metal floor. It's unlikely to be metal, but there could be some sort of plate near a doorway. Oftentimes, businesses where you load something they'll normally have some sort of a stone or formica, some kind of a strong plastic floor. But then near the boundary, the stoop, or where the trucks load and unload, they'll have metal. So maybe this box is on the metal, and this person is just doing the final push from the floor of the factory to the back of the truck. So the coefficient of static friction then would be 0.5. Notice it doesn't have any units, and that makes sense because with the forces, frictional force is going to have a unit of newtons or pounds, and normal force is going to have units of newtons or pounds. Typically, there are other units of force as well. So that means that this mu has to be dimensionless. So the maximum pushing force to move this 120 kilogram box, so formula-wise, this is pretty straightforward. But we'll certainly do it anyway. So if we just draw our box here, so we've got the floor pushing up, we've got the earth pulling down, we've got the person pushing, that's the applied force, and then we have the frictional force. So just as the box starts to move, go from stationary to not stationary, Fs is equal to Fs max, which is going to be equal to mu sub s times the normal force. And this is asking what is the maximum pushing force needed to move the box. And then the maximum pushing force would be equal to this Fs max. All right, so in this case, so here if we look at some of the forces in the y direction, let's just say we have our typical xy axis here. That's not a very good looking y. Why is it not a good looking y? I do not know why, said the fly. So this is just another way of saying the net force in the y direction. We've got the normal force is pointed upward, the weight pointed downward, equals MAY, and there's no up or down acceleration, so that's equal to 0. Weight equals m times g, so N equals m times g. And that means that the maximum applied force is equal to Fs max, or as I like to say now, Fs max. So all I did was simply put this in for N. So now what we need to do is to figure out what the maximum pushing force is. And as I said, I just copied a portion of the table here. Actually, can I find it in the book? Yes, I'm looking at the book, and it doesn't really seem that anything else on the table in the textbook would be a better choice. Yeah, I guess the next obvious one, shoes on wood. That's an interesting one. So that'd be basketball players or some other indoor sport players. So I'd say that the best choice here is probably metal on wood. You can go to websites now that will have thousands of different coefficients of friction, or if your parents or grandparents were engineers, they would have actually looked in books, many, many pages of numbers with all sorts of exotic combinations of different types of metal on different types of wood, for example. So metal on wood, we'll just go with that, 0.5 times 120 kilograms times 9.8 meters per second, and we multiply all those things together and we get 588 newtons. Okay, so now what's the acceleration if we keep up this push after the box moves? Okay, so we're going to keep up this push right here. So this is the second part. Let's just use a different color because it's just the second part. Blue seems pretty good. I did use blue up here for the axis, but that's okay. All right, well, N is going to be the same. W is going to be the same. F applied is going to be the same. So you might say to yourself, what's different? So that's a question. I'm going to ask that in a different color. What's the difference between this part and the first part? Well, in this part, the object is moving. So we have a different type of friction. And that's called kinetic friction. Abbreviated F sub K. F sub K is also proportional to the normal force. Or we can change that proportionality into a constant. F sub K is equal to mu sub K, some coefficient, times the normal force. So if we look back on the table, we see that the coefficients are different numbers. The coefficient of friction of metal on wood is 0.5 for static and 0.3 for kinetic. And notice there's a difference for all of these. So rubber on dry concrete, that would be like a tire on a road. Rubber on wet concrete. So actually, it gives you a good indication of why it takes longer to stop on a wet road, because the coefficient of friction is less on a wet road than a dry road. So everything else being equal, that frictional force, which would be the stopping force, would be less on wet concrete than dry concrete. So same with your bike. Most roads aren't made of concrete. That's too expensive. And concrete's brittle and doesn't really change as much with the temperature changes. But certainly sidewalks, so if you're riding your bike, same sort of thing. So if we keep the same force, and now I've got enough of a color boundary, I can do this. Oh, actually, let me quickly finish with the blue. So now, let's actually change that a bit. Because the frictional kinetic force is going to be less. So Fk is less than Fs max. So if we look at the sum of the forces, or the net force in the x direction, we've got the applied force minus Fk equals m times a. And we want to know the acceleration. So that means that a equals F applied minus F sub k. And let's just quickly note over here, F sub k is mu sub k times the normal force, or in this case, minus mu sub k mg divided by m equals a. And if we plug those numbers in, we come up with 1.96 meters per second per second. So that means if you keep up the same push that you needed to use to get it moving, if you keep up the same push, so this same maximum applied force, you would actually cause that object to accelerate. So an interesting way to see this is if you have a bathroom scale, or you can actually use a spring scale. So those of you that have the lab kit, there's a spring scale in there. But you can use this with the bathroom scale as well. So hook the spring scale onto something, maybe a textbook, or a binder that has maybe a little ring that you can put the hook into. And tug the spring scale along. And you'll notice that the spring will stretch a little bit. It'll read a number. The book won't move. But then all of a sudden, the book will go from stationary to not stationary. So there's acceleration. And if you keep up that same pull, let's say at 3 newtons is when it starts to move, you keep that up, you'll actually notice that the book speeds up. If you just want it to get going a little bit, you'll notice as you pull the spring scale that from when it's stationary to just when it starts moving, the reading on that scale will go down. So you can do that. You can have someone sit on a chair and push them with a bathroom scale. That works as well. So let's look at the skier problem again. We've looked at this in a couple other situations. First, just to set up a diagram. Then we actually found something from it. Now we're going to find some more information. So now we want to know what is her speed after sliding 50 meters from the bottom of the hill. So we still have that 25 degrees, and we have that because this is the picture I copied from the book, and I was too lazy to do some sort of Photoshop to change that angle. And now we're just going to, before I gave you the height of the hill, now this is going to be a different hill, even though the skier is wearing the same clothing. They're going down a 400-meter long hill. And we want to know her speed after sliding 50 meters from the bottom of the hill. So I've got my free body diagram here. So let's look at this situation. First, we'll do the sum of the forces. So let's go with black here for most of the work. So and I'm not going to plug in the numbers, certainly not for a while, and maybe not ever, sort of depending on the time. So the net force in the x direction, so I'm going to actually say that down the hill is a positive acceleration. So I'm going to switch up a little bit our coordinate system. So first it's going to be tilted. So up is positive and left is positive. So some of the forces in the x direction, we're going to have F here. And we're going to have this component of the weight. So what are those going to be? So this is going to be, so this component of the weight is going to be, here we've got our same angle theta. We have, that is the opposite, so that's going to be mg sine theta. This is mg cosine theta. All right, so we've got mg sine theta minus f equals m a sub x. So we want her speed after sliding 50 meters from the bottom of the hill. So let me put down here, well, I should have actually started with that. So we know here so her speed at the top, I guess we don't know that for sure since she goes down the side of a 400-meter long hill. So she starts at rest. We're going to have an intermediate step at the bottom. We don't know what that is. We don't know what that is, but that's going to be her target variable. We're going to have a duration on, or I'm sorry, a displacement on the hill. It's equal to 400 meters. We're going to have a displacement at the bottom that's 50 meters. That just comes from that right there. This person has some sort of acceleration down the hill. And on the next slide, I'll continue with sort of the second half of the drawing. So first off, we need to figure out her velocity So we need her speed after sliding 50 meters from the bottom of the hill. So we want and let me actually draw that now. So let's label this a little bit better. So here's V0, here's V1, here's V2. This is delta X2, delta X1, here's A1, and then down here we're going to have a different acceleration. That's going to be A2. So this is our target. This is the initial speed at the bottom of the hill. Well, in order to find that, this initial speed at the bottom of the hill, this is also the final speed yeah. Of the downhill portion. So basically the person slides down the hill. So let's go to the next one here. So they start at rest, they pick up speed and get to the bottom of the hill. Then they slide along the ground, and while they're sliding along the ground, they actually are slowing down because there's still going to be friction between the skis and the snow. And we can look up that number to help us out with that. So the net force in the x direction, we have this right here. Well, so this is equal to MA1. So we don't know A1, we don't know M. Let's just underline all the things we don't know. So we don't know this, we don't know that, we don't know that, and we don't know M, but we've already underlined that. So we can get some help though, just like with projectile motion, the two dimensions are independent of each other. So we can look at the net force in the y direction. So we have n upward minus mg cosine theta downward. And since we have a tilted coordinate system, the acceleration in the y direction is 0 because that person's not moving up out of the hill, or they're not sliding down into the hill either. So that equals 0. All right, and we also know that the kinetic friction force is equal to mu sub k times the normal force. So we can combine these things here. So we can move this into this equation, mg sine theta minus mu sub kn equals ma1. But notice here that n is equal to, so that's related to f sub k, but it's also related to m times g times the cosine of theta from this. So n equals mg cosine theta, and we can plug that into this, so we get mg sine theta minus mu sub k n, which is mg cosine theta equals ma1. And if you look here, let's use a different color for this. The m's cancel out, and we end up with a1 g sine theta. So we end up with minus mu sub k g cosine theta equals a1, or v1 squared equals v0 squared plus 2a delta x1. Well, if they start from rest, then that equals 0. So v1 squared equals 2 g sine theta minus mu sub k g cos theta times delta x1. All right, so this is an acceleration term times a displacement term. So that's our velocity at the bottom squared. And one of our lab activities, you actually did a simulation where you had the box slide down the hill, and you noticed that the amount that it slid did not depend on the mass. And notice here the velocity at the bottom, so v1 doesn't depend on mass. And then it depends on the angle in this sort of weird trigonometric way. Okay, so now the skier is sliding along the bottom of the hill. So now the earth is pushing them up. The ground is pushing them up. The earth is pulling them down. And you've got this force of kinetic friction. So that means you've got a different acceleration. And notice that this acceleration is actually in the opposite direction. So it opposes the motion. So going down the hill, the acceleration was down the hill. On the flat surface, the acceleration is in the opposite direction of the motion. So let's look at the forces again. So if we look at net force in the x direction, we're going to get because we decided that this was the negative direction, so negative F sub k equals m2. We know that F sub k equals mu sub k times the normal force, and from the net force in the y direction, we could almost do this without writing an extra step, but that's just going to be n minus mg equals 0 because it's not accelerating up away from the ground or down into the ground. So that means that F sub k equals mu sub k mg. So negative, if we plug that into there, we get negative mu sub k mg equals m a sub 2. Masses cancel out again. So at the bottom of the hill, we had V2 squared equals V1 squared plus 2A2 delta X2. And notice up here, let's use the finger. So notice here I left it as a squared term. That's because I knew that we were going to be using it as a squared term. I could have said the V1 equals the square root of 2 times that difference there. But I knew that we were going to be using it as a squared term. So V2 squared equals V1 squared, so that's the 2 g sine theta minus mu sub k g cosine theta delta x1 minus 2 mu sub k g delta x2, where this is A2. All right, so we could plug things in there, and let's see, I haven't actually plugged it in yet. But I like doing this, so notice that I haven't plugged in the numbers. I mean, that's important enough to write down. So V2 squared, if we plug that in, I apologize for not doing this in advance, so 2 times that quantity, 9.8, times the sine of 25, minus, so we coefficient of friction. Probably the best one here, waxed wood on wet snow, maybe. So kinetic friction is 0.1. Minus 0.1 times 9.8 times the cosine of 25 times, and now delta x1 is the 400 meters down the hill. That's going to be subtracting off then 2 times 0.1 times 9.8 times, and we want to know after 50 meters. Oh, so interesting. So I may have plugged in a number incorrectly here because I actually got a negative number. So I'm going to have to work on that. You could plug it in at home and see what you get. But I'm going to go on because that algebraically is the right solution. So I'm just going to make a note here. When I plugged in the numbers live, I actually got a negative number. So you can check later, or if anybody's watching wants to do that, and I'll have this on the course website and then also on YouTube as well. So if you want to make a comment with the proper number, that's good. It's also possible that I did this quickly before, that one thing, although I got a huge negative number, not a huge, but a bigger negative number than you'd think. So it's possible that if I picked a number that was too large here, that actually the object would stop before 50 meters. If I picked, say, 10,000 meters, well, coming from the bottom of the hill with that friction at the bottom, it's not going to slide 10,000 meters, right? That's 6.2 miles. So if I pick too large of a number, then we're going to get a nonsense here because the object was stopped before it reaches that displacement, before it's traversed that displacement. So actually I'll work on this later, and I'll do an addendum. Actually, I think it is time now to stop. So what I'm going to do is I'm going to stop the recording. I'm going to plug in the numbers again and then see what I get. So I'll stop the recording for a bit and then I'll start. So people who are watching right now, of course, can still watch, but if you're watching the recording after the fact, time will magically go away. Okay, I'm back. Yeah, I don't know what I did before because I cleared out my calculator, so I don't see what I did. So I did check later. Actually, I wonder if there's a way that I can, there we go. So this time, I purposely picked a number here that was really large. So when I do this, I get about 2,600 meters squared per second squared. So that means V2 equals 50 meters per second, which is crazy fast. Okay, the time is up for today. There's one other problem that I wanted to work on, and I actually have something else to do right now, but I'll probably come back and do a bonus recording. So it's like an extended track that will be going over that additional problem. So thanks for watching, and hopefully you got something out of it. Let me just quickly actually review what we went over. So we've got the new formulas here, the new frictional formulas that I have circled. And we still use our old force formulas as well here. So we still use those. Now we also use these as well. And that force formula how interesting. I wondered what happened there. When I was moving this around, I switched the pages around, and that was kind of weird. So we have the person pushing on the box. The frictional force is not a specific number. The harder you push on the box, the greater the frictional force up to a point, and then once the box starts moving, then that frictional force just goes from static friction to kinetic friction. There's a certain characteristic, though, that doesn't change, and that depends on the two materials. And here was a very extensive problem. It took a lot longer than I had originally predicted, so I apologize for that. And I especially apologize for not plugging in my numbers properly. But we went through the sum of the forces in the x direction. We had a bunch of unknowns, but we remembered that we know what the frictional force is. That depends on the normal force, so then we did the sum of the forces in the y direction. So the two things that I've underlined in red and circled in red, they combine together to produce this acceleration while going down the hill. And our final number then is this right here. So this again is that acceleration. And then here's our final formula for velocity. And again, we had that question with the lab activity. How does the distance it slides relate to mass, and how does it relate to angle? Well, notice there's no mass, so this is independent of mass. And it does have a sort of an odd dependence. So a non, I don't know if I want to say odd, that's a value judgment, but it's got a non-straightforward theta dependence. So if there's one lesson that you can take from this equation here, or I'm sorry, from this recording, is the careful notation here and the careful describing of the formulas, and also how a lot of things will cancel out. So I didn't even say what the mass of the skier was. Turns out at the end of the day, it didn't matter what the mass of the skier was. It was independent of that. All right. Thank you for watching, and hopefully you learned something.